Let's continue the discussion. The next definition. We define the absolute value function. The absolute value of a number a in R in the set of real numbers is a number we denote it by absolute value of a. It is equal to a for a greater than or equal to 0, and negative a for a less than 0. Okay, so once we have this definition, sometimes we also call it a piecewise defined function. When we have this definition, we will quickly have the remark. The absolute value function is multiplicative, which means it is compatible with multiplication, i.e., absolute value of the product is the product of the absolute value for all a, b in R, for all real numbers a and b. Okay. Well, let's try to prove it. So far, we don't have a lot of tools, so we have to study the cases. So we consider four different cases. Case 1. If a is 0 or b is equal to 0, it's the simplest case. When a is 0 or b is equal to 0, so a equal to 0 or b is equal to 0, it is included in the first case. So from here, actually, before we do the remark, we can see that absolute value of 0 is equal to 0. So that's something you need to keep in mind. If a is 0 or b is equal to 0, then a times b is definitely equal to 0. This is actually if and only if situation. A0 or b equal to 0 is equivalent to say the product is equal to 0. So let's check the left hand side. Absolute value of a times b is absolute value of 0, which is 0. And right hand side, you have absolute value of a times absolute value of b. Then from this condition, we know that this is also equal to 0 because absolute value of 0 is also equal to 0. Then one of the factor is equal to 0. The product is 0. Hence, absolute value of a is equal to absolute value of a b is equal to 0 is equal to absolute value of a times absolute value of b. Right? Okay, this is the trivial case. Second case, we see a pair of positive numbers. For positive a and positive b, then we know that we know that the absolute value of a is equal to a, absolute value of b is equal to b. Also, we know that, you see, b is a positive. This is inequality. You multiply the inequality by a positive number. You keep the direction. So we also know that the product a times b is a positive. And then absolute value of a times b is equal to ab, is equal to absolute value of a times absolute value of b. Right? It's computation. It's not the equation, step-by-step equation. It's not that way. All right? So, case 3. A greater than 0 and b less than 0. Or a less than 0 and b greater than 0. So those two situations are pure symmetric. So you can say the following. In the textbook, it says by symmetry. You can also say without loss of generality. Without loss of generality, we assume that A is greater than 0 and B is less than 0. Assume this. All right? If you have the second case, you just exchange the place of A and B, then you will have the same proof. So that's why we say without loss of generalities. And A is positive, B is less than 0. Then we know that you multiply this inequality by a positive number. AB is less than 0 times A is 0. AB is less than 0. So absolute value of AB is equal to negative A times B. Okay, so absolute value of a negative number is negative of this number. And absolute value of A is A because it's positive. Absolute value of B is negative B because B is negative. So A times absolute value of A times absolute value of B is A times negative B. Remember, this is A times negative 1 times B. You can exchange it's a commutative product. So it's negative 1 times A times B, and it's negative AB. Negative AB is absolute value of AB. Correct? So you still have the same equality. Okay? Case 4, we have a negative and a negative number. If we have a negative number, then remember you have inequality, you multiply the inequality by a negative number, then AB is going to be greater than 0. You have to change the direction of this inequality because you multiplied by a negative number. Okay, so A times B is positive, absolute value of AB is equal to AB itself. And absolute value of A is negative A, absolute value of B is negative B. So absolute value of A times absolute value of B is negative A times negative B is negative 1 times A, negative 1 times B. You will have negative 1 squared times AB. We know negative 1 squared is positive 1, so it is equal to AB, which is absolute value of A times B. So we are done. So you see here we classify the situation into 4 cases, and for each one we directly apply the definition of a absolute value function, plus we have to determine the sign of a product. How do you determine the sign of the product? You will apply that multiplicative property from the order axioms postulate 2. All right. Okay, so this is the remark right after the absolute value function. It is multiplicative. Next, let's relate the inequality involving absolute value function to the regular inequality. Let A be a real number and M non-negative. Then absolute value of A is less than or equal to M if and only if negative M is less than or equal to A, less than or equal to capital M. Alright, so this is an if and only if. In the future, whenever you see if and only if proof, it means you're going to prove 2 directions. From one statement, you get the other one, and from the other statement, you get the original. So you have 2 parts. First, suppose that ops value of A is less than or equal to m. Ops value of A is less than or equal to m. Well, this one, if we multiply it by a negative number, -1, remember that -1 is less than 0. We proved it. -1 is less than 0. So we multiply this inequality by negative number. We're going to change the direction. So negative ops value of A is going to be greater than or equal to -m. This is the result directly from the original assumption. Okay, now let's study case 1. A is here. See, A has a condition ops value of A is less than or equal to m. If A is non-negative, A is greater than or equal to 0, then what we have? Ops value of A is equal to A. The same thing, ops value of A is less than m, so this whole thing is less than m. A is greater than or equal to 0, of course, it's between this. And m is greater than or equal to 0. So negative m is less than or equal to 0. Negative 0 is still 0. Negative 1 times 0 is 0. So negative m is less than or equal to 0. So you connect these two, you will get negative m less than or equal to A. So here 0, 0. You drop it. So negative m is less than or equal to A, less than or equal to positive m. So for a non-negative number A, you prove this inequality. Right? So here you apply the definition of ops value, and then you also apply the property of a positivity of m. Okay, and then you use the transitivity. You connect or join the two inequalities. So for for non-negative numbers, the statement is correct. Let's see the negative numbers. When A is less than 0, then ops value of A is negative A. Absolute value of A is negative A. And negative ops value of A is equal to A. You multiply two directions by -1. You see, remember that the inverse of the inverse is the original one. You put inverse on two sides. The right hand side, you will have negative, negative. See here, if we put inverse of the inverse, this one is equal to A. It gives you the right hand side. All right, so A is equal to negative absolute value of A. Negative ops value of A, here we are going to use. So A is equal to negative ops value of A. A is less than 0. See? So here is an equality, it's an inequality, and negative ops value of A is greater than or equal to negative m. So we do have the left half, 0, m, whereas m is here, so it's less than or equal to m. So we build the inequality. So we have the inequality. So for the non-negative number, for a negative number, we prove the same result. So from the ops value of A less than or equal to m, we can get negative m less than A less than positive m. All right. Okay. That is just one direction. You start from the first statement, you can get the second statement. And if and only if means you also need to assume the second statement and then you get the first statement. Okay, so conversely. Assume that A is between negative m and positive m. is between negative m and positive m. And this chain of inequality, it means negative m is less than or equal to a, and a is less than or equal to positive m. All right? So this one is okay. Let's check this one. Negative m is less than or equal to a. We multiply multiplied by negative 1. Negative 1 is less than 0. We have what? We have m is greater than or equal to negative a. You multiply it by a negative number, you're going to change the direction of inequality. Negative of negative m is positive m. A times negative 1 is negative a. Okay, so these two cases, these two conclusions both correct because we assume this. Okay, now let's see. We're talking about a. If a is positive, if a is a positive, then absolute value of a is equal to a. A is less than m. And that's it. So we get the first one. If a is negative, absolute value of a is negative a by definition. Negative a is less than m, less than or equal to m. So we also have this. So put these two things together. So for all a in R, absolute value of a is going to be less than or equal to m. Right? Here we can include the 0. If a is equal to 0, 0 is less than m because of a condition. Right? So from the second statement, we do the cases discussion, we get the first statement. First implies second, second implies first, then we have if and only if. All right. Okay. Next. Next, let's see the positive definite, symmetry, and the triangle inequality. That's also very important, the fundamental property of a ops value. The absolute value satisfy the following three properties. First, so-called a positive definite. For all a in the real set, absolute value of a is always greater than or equal to 0, with absolute value of a equal to 0 if and only if a is equal to 0. Okay, so positive definite, and it is 0 if and only absolute value is 0 if and only if the original input is 0. Second, symmetric. For all AB in R, A minus B ops value is equal to B minus A ops value. So you can exchange the exchange the terms among between the inside the difference, you still have the same ops value. It's a symmetry. Third is a triangle inequality. For all AB in R, A plus B ops value is always less than or equal to the ops value of A plus ops value of B. And A minus B ops value is always greater than or equal to ops value of A minus ops value of B. And ops value of A minus ops value of B is always less than or equal to ops value of A minus B. It looks like tongue twister. Okay. Anyway, let's first see it. Let's see how to prove it. And later we will see the geometric idea about the triangle inequality. First, we're going to prove the positive definite. If A is non-negative, then by definition, ops value of A is equal to A, so it's greater than or equal to 0. If A is negative, then negative A is positive, right? Remember that we know that you multiply this inequality by -1, you change the direction. And then the ops value of A for the negative A is equal to negative A. For a negative number A, it is equal to negative A. Negative A is greater than 0. So for both cases, ops value of A is always greater than or equal to 0. All right. Okay, and later let's prove that ops value of A equal to 0 if and only if A is equal to 0. So if A is equal to 0, then ops value of A is ops value of 0 is equal to 0 by definition. Right? So this has no problem. And if ops value of A is equal to 0, then what do we have? Ops value of A is either equal to A or equal to negative A. So then by definition, plus or minus A is equal to 0. Okay, either plus or minus of A is equal to 0. And let's check. Then this A is equal to 1 times A. 1, remember 1 times 1 is 1. -1 times -1 is 1. So put them together, we can say plus or minus 1 squared times is equal to 1. So this plus minus 1 squared times A is equal to A, because this is 1, the multiplicative identity. Okay, so we put plus minus 1 times plus minus 1 and times A. This product square means you have 2 copies. And then you combine these two factors together, you will have plus minus 1 times plus minus of A. And we just know that plus minus of A is equal to 0. Is equal to 0. So this term is 0, you will have plus minus 1 times 0. 0 times whatever number is equal to 0. So you get A is equal to 0. Alright? A is equal to 0. So this is the proof. How do we get ops value of a equal to 0? How do we get a equal to 0 from ops value of a is equal to 0? All right? Second part, symmetric. The symmetric property comes from this observation: a minus b is negative b minus a. And you put ops value, this is negative 1 times b minus a. So let's put negative 1. And the ops value function is multiplicative. It's ops value of negative 1 times ops value of b minus a. Ops value of negative 1, by the definition, it is equal to 1. So it's 1 times b minus a is ops value of b minus a. All right? It's not that bad. Okay, so to prove the triangle inequality, it will take some writing. Okay. So first, let's prove the triangle inequality. This one. All three are called triangle inequality, but usually this one is preferred. The first one is preferred. So we notice that for all x in R, ops value of x is less or equal to ops value of x. Because you have this equal sign, so this is always correct. All right? So you see, remember that ops value of a is less or equal to m is equivalent to a is bounded by negative m and positive m. This is the theorem, the remark we just proved. All right? So here you consider this one as capital M, this x as a. So this x is bounded by ops value of x and the negative ops value of x. Okay, see, you have this identical terms, but you have to understand them in different way. Okay, so this works for all x in R. Now let's check. Then x equal to a and x equal to b. We have a between negative ops value of a and ops value of a. B is between negative ops value of b and ops value of b. The inequality. And then we add these two inequalities part by part, left part by left part, middle part by middle part, and right part by right part. Correct? And this one, if you write it, it's a effect out a negative sign. And you will apply this property again. This moment, this a becomes this a plus b. This m becomes ops value of a plus ops value of b. We know this one is non-negative, greater than or equal to 0. Because each of them is greater than or equal to 0. You add them together, it is still greater than or equal to 0. Okay, so a is bounded by negative m and positive m. So ops value of a plus b is less than or equal to ops value of a plus ops value of b. You see, we just use this remark and we get the detailed proof. All right? Okay, so this is a triangle inequality. For the second inequality, let's see what is the second. The second inequality is this. A minus ops value of a minus ops value of b is less than or equal to a minus b ops value. So second, ops value of a minus upper value of b. We're going to write it as no, the other way. A minus b plus b minus upper value of b. So we subtract b and add b. We do not change a. The second term we just copy. And for this one, we apply the triangle inequality. So upper value of a minus b plus upper value of b and minus b. You apply the triangle inequality from the first part, from what you just proved. You consider a minus b as one element and b as a second element. And upper value of b minus upper value of b cancelled, so it is equal to. See, the difference of the absolute value is less than or equal to the absolute value of the difference. All right. So here you need some creative idea. Need the creative idea. Okay. Okay. So let's check the other one. We are going to show the third inequality. What is the third inequality? If you put upper value is less than upper value of a minus b. Here you don't have upper value. It is less than or equal to upper value of a minus b. You put upper value, it is still less than it. Okay. So third, let's copy it. We need to prove that upper value of a minus upper value of b is less than or equal to upper value of a minus b. So this is what we need to prove. And you consider this as a number, and this is capital M. It is equivalent to upper value of a minus upper value of b less than or equal to capital M greater than or equal to negative capital M. Okay? Greater than or equal to the negative capital M. And this is what we need. The whole thing is what we need. We actually already checked this the second inequality. So we only need to show that negative upper value a minus b is less than or equal to upper value of a minus upper value of b. Okay, so we need to show this. We need to show this. What else? Okay, then let's switch. I don't want this negative sign. It's also equivalent to, you have a negative sign. You multiply this inequality by a negative number. I want to cancel this negative sign. If I cancel this negative sign, I need to switch the inequality. So it becomes negative upper value of a minus upper value of b, which is upper value of b minus upper value of a. Okay? And we also know that upper value of a minus b is equal to upper value of b minus a. This is what we know. So we actually need to show this part, upper value of b minus upper value of a is less than or equal to upper value of b minus a. Check that. This is exactly the statement, the second inequality. This is the second inequality. We are done. We already proved the second inequality. So we are completely done. Okay. So that's all. The triangle inequality. The triangle inequality. The reason this inequality is called the triangle inequality is the following. If you study a little bit geometry, you will see that in the plane, we can have something so-called a vector. Vector is a segment with a direction with the initial place. And the absolute value is actually the length of this segment. The addition here, because we use addition, let's see where. Yes, addition here. Addition is actually this way. You have a vector A, you have a vector B. How do you construct the addition A plus B? You put the second vector with the initial point as the terminal point of the first vector, and then you connect the initial point of the first vector and the terminal point of the second vector. This is A plus B. Sorry, my bad. So this is the initial first vector. This is the initial point, terminal point. You place a second vector, initial point coincide with the terminal point of the first vector, like the chin. You start from here and draw the second vector. And its sum, A plus B, means you start from the initial point of the first vector, you stop at the terminal point of the second vector. You draw it like that. This long stuff. And in the triangle, we know that the sum of two sides, the length, here we are talking about the size of a triangle. The size of a triangle is measured by the ops value. We call it ops value. The sum of two sides is greater than the third side. If you really have the triangle. If you have the degenerate triangle, they belong to the same line. It can be equal. For example, if you have A, then you have a B, then the total will be A plus B. You see, in this way, you do not have a real triangle, you have a segment. This is the degenerate case. In the degenerate case, you have equality. If you do not have degenerate case, you have a inequality. Because of this geometric meaning, so we call this inequality the triangle inequality. Anyway, you will see this repeatedly many times later. But here I just want to tell you why we call it the triangle inequality. It has such geometric meaning. All right. All right, let's see some simple examples about this triangle inequality. So see the example. Prove that if -2 is less than x less than 1, then ops value of x squared plus x is less than 6. All right, so prove. X is less than is greater than -2 less than 1. Less than 1. 1 is less than 2. So x is bounded by -2 and +2 implies ops value of x is less than 2. Okay, so it's not exactly equivalent to the original statement, but the original condition, but you can get this result. All right. Okay, then ops value of x squared plus x by the triangle inequality is less than ops value of x squared plus ops value of x, and this is a ops value of x squared and plus x. You can show that, remember, ops value of x is less than 2, then x squared, ops value of x squared is less than 2 squared. So this one is less than 4, upper value of x is less than 2, so the sum is less than 6, and that's it. That's as simple as possible. All right, so it's not a creative example, just tell you to apply the, try to apply the triangle inequality, okay? And next, let x, y, a be real numbers. 1, x less than y plus epsilon for all epsilon greater than 0, if and only if x is less than or equal to y, I'm sorry, x is less than or equal to y. So this is a very, very useful strategy. Sometimes we cannot directly prove x is less than or equal to y, but we can prove that whenever you increase a little bit, x is going to be less than y plus epsilon for whatever positive epsilon. Then it is equivalent to prove x is less than or equal to y. Okay? Symmetrically, x is greater than or equal to y plus epsilon for all epsilon greater than 0 if and only if x is greater than or equal to y. Third, absolute value of a is less than epsilon for all epsilon greater than 0 if and only if a is equal to 0. All right, so let's try to see the proof. So you see here, after 2 lectures up to this moment, the analysis involves a lot of proofs. The calculus involves a lot of computations. So you learn how to compute, you learn the reason behind the compute in the analysis. Okay. Suppose, let's see the first one. We're going to use proof by contradiction. Suppose that x less than y plus epsilon for all epsilon greater than 0. The first statement is correct, but x is greater than y. It's not, the conclusion is not correct. Conclusion says x is less than or equal to y, but here you assume x is greater than y. Okay, then set epsilon 0 equal to, okay, x is bigger, y is smaller, so x minus y. And this is greater than 0. Then this implies x is equal to y plus epsilon 0. X is equal to it. Then x cannot, it is not true that x is less than y plus epsilon 0. You have an equality, then by the trichotomy property, this holds, then this one cannot hold. Right? It is less than, equal, greater than. 3 cases, only one case. One and only one case can happen for 2 numbers. Here this case happened, then this one does not happen. Then you see here, you get some obvious wrong stuff because you suppose x less than y plus epsilon for whatever epsilon. This contradicts. The hypothesis. for epsilon equal to epsilon 0. Hence this part is wrong. The first part is always correct because it's part of the hypothesis. What you assume is this. Your assumption is wrong, so x is less than or equal to y. This is one direction. From the left side, you get the right side. Okay. Conversely, suppose that x is less than or equal to y, and epsilon is greater than 0. X less than or equal to y, then you have two situations. Then either x is less than y or x is equal to y. For x less than y, they use the following chain. You see, x plus 0 less than y plus 0. The plus the same thing. And 0 is less than epsilon because of this. So here you consider 0 as a fixed yes, you consider 0 as a fixed point, x and y as a two this way. You consider x, y as an inequality, you add a constant number 0. This part, you consider y as a you consider 0 and epsilon as an inequality, y, you add a constant y. Let me say it. You have 0 less, you have x less than y, you add a 0, add a 0. You have 0 less than epsilon, you add a y, add a y. Okay? So that's why they need the mid step, y plus 0. Okay, so x less than y plus epsilon. X less than y plus epsilon. For x equal to y, then x is equal to y and it is less than y plus epsilon for sure. That's the same thing. Y is y less than y plus epsilon. So you have the same thing. So we prove the first statement. My bad here. This is subtraction, not addition. Okay, so this is the complete proof for the statement 1. All right? Okay, so in the book, there are complete proof for the statement 2 and the statement 3. So far, I'm not going to repeat them. They're very close to the statement 1. But what I want is that you try to prove it by yourself without consulting the textbook. See if you can prove part 2 and part 3. If you couldn't, you go back to the textbook and read it and try to understand which part you couldn't pass. Okay? So do the proof for the part 2 and the part 3 by yourself and check it with the textbook. Okay. Okay, then next, let's close the section with the interval. Okay, so the closed interval could be interval AB. It means the set of all x such that x is greater than or equal to A, less than or equal to B. This is closed interval. or from a to infinity, it's a set of x such that x is greater than or equal to a, or from negative infinity to b, it's a set of x such that x is less than or equal to b, or negative infinity to positive infinity. It's just x belongs to R. So they are closed interval. We are talking about closed interval, not closed set. Open interval. Open interval, we just use parentheses. The set of x such that x is between a and b without equality. And here it's from a to infinity. It's a set of x such that x is greater than a. And from negative infinity to b is a set of x such that x is less than b. And negative infinity to positive infinity is a set of x for all x. So you can see that this negative infinity to positive infinity, it is open interval, it is also a closed interval. Okay? Except the closed open interval, you may see the half open, half closed interval. For example, it's just one of a possible case. For example, you have a bracket A and a parenthesis B, braces B. So it is a set of x such that x is greater than or equal to A but less than B. Okay, so whenever you see the brace, it does not include the equality. When you see the bracket, it includes the equality. Okay, so they are all of them are called intervals. And for an interval, is bounded if it does not include infinity. If you do not see the infinity, it's bounded. If and only if it has forms AB brackets, braces AB, half open, half closed, something like this. Okay, for all the numbers not infinite, there's no infinity. And here AB are called endpoints. AB are called endpoints. And other intervals are called unbounded. So you have endpoints, they are bounded. And you do not have endpoints, it's unbounded. Right? And here, when you have an interval, of course, you will naturally believe A is less than B. Right? So if A is equal to B, then you will have just a point, one point. If A is equal to B, the 2 points coincide. The interval is so-called degenerate. Degenerate. Of course, if A is strictly less than B, it is non-degenerate. Non-degenerate. And you will see that if you have a degenerate case, if you have, for example, 1, 1 open interval, it's not just degenerate, it's empty, because 1, 1 endpoints are not included. But if you have closed interval 1, 1, it's actually only containing 1 point. So a degenerate open interval is an empty set. a degenerate closed interval is a point. Is a point. Okay. Okay. And for the bounded interval, whatever form, this is just one of the example. B minus A is called the length. Length of it. Okay, B minus A is called the length of it. Sometimes we just denote it like this. We must use a big number to subtract a smaller number. If you don't know which one is bigger, which one is smaller, you can use either of the form, but you have to do the ops value. Ops value is used to measure the length of the interval. Okay, and ops value of A minus B is also the distance between A and B in R. Okay, so that's it. That's the final stuff for the first section. Read the textbook and try to do this exercise. Okay, we stop.